Okay, so this is going to conclude section 2. I know it says part 4, but really for you guys it's part 3. That's why it's called P2C, ABC, third letter of the alphabet. So this is part 3, and we're going to be simplifying radicals. So here are some rules or some facts that you're going to be using. So when we simplify a radical that's not a perfect square or a perfect cube, especially for the perfect squares, what we're going to do is do a factor tree. So for example, here on this example for number 20, for the square root of 20. 20 is not a perfect square. If it's a perfect square, like say 16, you know you could just square root it and it becomes a 4. But if it's not a perfect square, what we're going to do is a factor tree. So we're going to find the factors or two numbers that would multiply to give me a 20. Now I could either use 2 times 10 or 4 times 5. It doesn't matter. Let's do 2 times 10. I'm going to keep breaking this down until I have prime numbers. I'm going to break down the 2. I'm going to break down the 10. And then once I have a row of all prime numbers, I look for pairs. When you have a pair of the same number, so I have a pair of 2s, the 2 comes out of the square root, and anything else that does not pair up stays under the radical. So the square root of 20 would be 2 square root 5. So as soon as you can pair up a number and make a pair, it no longer stays under the square root, it comes out. Now, whenever you multiply 2 square roots, the indexes must be the same. So that means you have to multiply a square root times a square root or a cube root times a cube root. If that's the case, you just multiply the numbers underneath. So 2 square root of 2 times the square root of 3 is just the square root of 6. Now, if that number, let's say instead it's 5 square root 2 times 3, let's do 4 square root 3. If you have a number outside and a number inside a radical, what you do here is you do the 2 outside numbers together. So I would do 5 times 4, and that would give me 20. And then I would do the 2 inside numbers together, and that would give me the square root of 6. So when you multiply numbers that have square roots, you always do whatever's outside together, and then whatever is inside together. Now for dividing, in order to divide, the index must be the same, so meaning I have to do a square root and a square root, or a cube root and a cube root. So if you get something like this, you can divide, because they're both under the radical. 10 divided by 5 is 2, and then the 2 stays under the square root. So let's practice breaking down non-perfect squares. So my first one is 28. Now I just want to show you that it doesn't matter what you start with, the final answer is going to be the same. So I'm going to do factor trees here. So I'm going to do 2 of them. The first one, I'm going to start with 4 times 7. I'm going to keep breaking it down until it's prime. So the 4 becomes 2 times 2, and then bring down the 7. Now that it's prime, I look for pairs. Notice I have a pair of 2s. Once you make a pair, just take away the square root symbol and bring the number out. Anything else that doesn't pair up stays underneath. Now, let's say instead you decided, you know what, I don't want to do 4 times 7. I want to do 2 times 14. It doesn't matter what you start out with. You're going to keep going until it's prime. And notice your bottom row on both of these is the same. Again, you have a pair of 2s. 2 comes out. 7 stays underneath. Why did I write a 3? There's a 7. So you can do it either way. It doesn't matter. Now, some numbers are going to have a whole bunch of factor trees you could choose to do. You don't have to show me everything. Just pick one way. Now, let me go back up here. Now, some of you are going to get, I guess, really good at this. And as soon as you can recognize that one of your factors is a perfect square, you could also square root this, because the square root of 4 is 2. 7 you can't break down anymore, and you could go right to the answer. All right, so some of you will get really fast, and you don't have to do all the way down to prime. Pretty good? All right, next one. Now, here's an example of one that's got a whole bunch of things you can do here. So for 48, I can decide to do 2 times 24. I could also do 3 times 16. I could also do 4 times 12. And I could also do 6 times 8. Now, just remember, it doesn't matter which one of these you pick. Now, because I do this so much, what I always look for is, I know my perfect squares, so I try to find one of these where one of the factors is the biggest perfect square. So like this one. If I realize that 16 is perfect, I could square root it and then put the 3. Now, I think most of you, or a lot of people, they always like to divide even numbers by 2, so they might pick that one. Another common one might have been this one. So let's do the 6 and the 8, just to show you that we're still going to get this answer. So I would break the 6 into 2 times 3, the 8 into 2 times 4, and then 2's prime, 3's prime, this 2 is also prime, but the 4 is another 2 and 2. So now I would go back and look for the pairs. So I have a pair of 2's here. So take it out of the radical. And then I have another pair of 2's over here. Take it out of the square root. And then I would leave the 3 behind. Now, somebody in the other class said, well, why can't you make a pair of these 2 2's? Because these are already outside a square root. So anything that comes out from the pair, you just go back and multiply them and then leave the 3 underneath. And it was the same answer I got when I found the factor that was the biggest perfect square. Try this one. Now we just did 48. Let's pick a different one to do. Let's do 4 times 12 on this one. Now also notice what's different is this number 2 is already outside. So this number 2 that's outside, it doesn't get to be included in looking for the pairs. It's just going to sit outside waiting for other numbers to come out of the pairs. So the 2's out. I'm going to start with 4 times 12. I'm going to break this down. I'm going to break it into 3 times 4. And then I can do the 4 one more time. Now let me bring this 3 down, this 2 down, this 2 down, and then this 2 that was outside. Now I have to go back and look for my pairs. So I have a pair of 2s. So this 2 that was already out comes down. I just made a pair. So out of here came a 2. Nothing to match with the 3. And then I have these pair of 2s that I can pull a 2 out. Now I can go back and multiply everything that's there. So these are all out. So 2 times 2 is 4 times 2 is 8. And then the 3 stays underneath. Let's try the next one. It's the 6 square root 45. So I need to break the 45 down. And I can do 9 times 5. Now, for those of you who realize 9 is a perfect square, you could square root it, multiply, and you're done. Now, if at this point you didn't realize 9 was a perfect square, then you got to break it down. 3 times 3. Bring these guys down. Now you have your pair of 3s. A 3 comes out. And then now you can multiply it and get the same thing. 18 square root 5. Let's try some more. Same thing. Just keep practicing this. This one gives us 14 and 75. So I have to figure out 2 numbers that'll multiply to give me 75. When I see 75, I think about quarters. I know that there are 3 quarters, make 75 cents. So I'm going to break it down into 25 times 3. Now again, if you realize 25 is a perfect square, you can make it a 5. And then the radical 3 didn't have a pair, or it's not perfect, multiply it and 70 root 3. If not, at this step, you would break the 25 into 5 and 5. Make your pair. The 5 comes out. And now multiply what's left. And you still get 70 square root 3. Okay. Can you guys still see the iPad screen? Okay. Next, number 6. Again, I got to figure out 2 numbers that'll multiply to give me 125. Again, I'm going to think quarters. I know that 5 quarters is $1.25. Again, if you realize 25 is a perfect square, pull it out, make it 5. If not, break it down. Make your pair. And now multiply what's left. And you get 50 root 5. Let's try the next one. Number 7. I need to find two numbers that'll multiply to give me 600. Again, there's a bunch, but I'm just going to do 6 times 100. Now, for those of you who realize 100 is a perfect square, you could square root it. 6, if you break it down, it's 2 times 3, no pairs there, and it would go right to 50 square root 6. Now, let's say you didn't know that 100 is a perfect square. Then again, at this step, you're going to break it down. 10 and 10, 2 and 3. Now, if you realize you have a pair of 10s here, you can also pull it out here. And then no pairs to make. So then this is when you multiply the two things that don't make a pair, you put them back together. And then these came out, so 50 square root 6. So if you end up with more than one thing that doesn't make a pair, multiply it back. Let's try number 8. Here we're multiplying just like I did on that very first slide with all that writing. Remember, you do outside with outside. So 5 times 2 is 10. And then you're going to do inside with inside. But look at my insides. They're the same number. So we've made a pair of 3s. So the 3 just comes out. And then you get 30. Now if you actually multiplied these two, you would have gotten the square root of 9. And then 9's a perfect square. And you still have to square root it. Anybody still need this slide? No? All right, let's go on. Oops. Number 9. Now, on problems like this, instead of, again, these are all under, instead of multiplying 5 times 5 times 9 and getting 225, and then I got to turn around and factor it, sometimes it's easier to factor it before you multiply it. Now, some of you may recognize that, oh wait, 225 is a perfect square and it's 15. But instead of multiplying it, what I like to do is leave it unmultiplied. So leave them apart. And then at this point, look for your pairs. So notice I've got a pair of 5s. So a 5 comes out. And then if you realize 9 was a perfect square, a 3 comes out, and then you multiply. And you still get the same answer as if you would have done 5 times 5 is 25, times 9 is 225. So you're better off not multiplying it because you're going to have to just turn around and factor it anyways. Try 10. Now, this one, again, I'm going to do the same thing. I'm not going to multiply 11 times 44. If I do that, I get 484. And then I got to turn around and factor it anyways. So instead, what you're going to do is you're going to take your 11, it's prime, the 44, I'm going to make it 11 times 4. And now look for your pairs. You got a pair of 11s, take it out. Now here you can either break this into 2 and 2 or realize the square root of 4 is 2, or make your pair, comes out, and you get 22. So if you multiply these, 484 is actually a perfect square. Next one, same idea. Let's not multiply and get 363 and then have to go back and factor it. Instead, this one's prime. This one factors. And now you have a pair of 11s. 11 comes out. The 3 doesn't have a pair, so you'll leave him underneath. Let's try number 12. Now we're going to divide or simplify fractions. Okay, so for here, notice the top has a square root and so does the bottom. I can simplify this fraction by dividing the top and the bottom by 7. So this becomes 6 square root 1 over square root 5. I'm basically simplifying the fraction 7/35, and it reduces to 1/5. Now the square root of 1 is 1, so this just becomes 6. And then you get a square root of 5 in the bottom. Now, there's a rule that states that you can never ever leave a square root in the bottom of a fraction. So what we need to do is a technique called rationalizing the denominator. And when we rationalize the denominator, I'm turning the denominator into a perfect square. And the easiest way to do that is to multiply the numerator and the denominator by the radical that was in the bottom. So notice when we go to multiply here, we now have a pair of 5s in the bottom. So the 5 in the denominator comes out, and the numerator just becomes 6 square root 5 over 5. If you think about it, this yellow square root 5 over square root 5, this is equivalent to 1. So technically, I've only multiplied by 1, even though it does change the whole setup of the problem. All right, let's try another one where we're going to reduce the fraction first, and then we're going to have to rationalize. My battery's going to die, so I need to charge. Okay. Let's go over to number 13. So for here, I'm going to reduce 48 over 39. I can divide both of these by a 3. So then this would become 5 and 16 over 13. 16 is a perfect square, so I can square root the 16, and out of the square root comes a 4, but the 13's still in the bottom. I'm going to multiply the top. Now, here we go again. We got to use that rule. We can't leave a square root in the bottom, so I have to rationalize. So I'm going to multiply the top and the bottom by the square root of 13, because again, remember, it's making a pair down here. So then the 13 gets released out of the radical, and then the top, this number is out, this number's in, so I just write them side by side. I don't multiply them together. Generally, the radical will always go second. Think of it like a variable. Pretty good on this slide? Anyone still need it? All right, let's go on to 14. Okay, so now on this one, we're going to apply our distributive property. So I'm going to distribute the square root of 5 to the square root of 5. So remember, whenever you multiply the same radical to the same radical, we've made a pair of 5s. So when I distribute it, this gives me a 5. Then when I distribute the square root of 5 over here, notice this one's not under the radical. So all I'm going to do is write them side by side. Again, put the radical second. And then the number that's outside the radical, write it first. You cannot subtract 5 minus 2 because this 5 does not have a square root of 2. Square root of 5. When you add and subtract square roots, think of them like variables. So in order to add or subtract, this 5 in the front would have needed to have a square root of 5 in order to do this, to turn it into this. So because this does not have a square root on it, this is how you leave your answer. So it's sort of like adding a 2x plus a 3x. You just add the numbers in front. So in order to add radicals, they have to have the same square root. Let's try the next one. So for 15, I can do this two ways. I can either decide, and I'm going to show you the better way, the harder way I think is to multiply it the way it is. So this is what you might be tempted to do. You might be tempted to say, okay, I'm going to multiply all the outside numbers and get negative 18, and then go back and multiply all the inside numbers, and then you get the square root of 432. Now, we still got to go back and factor it. So I could break this into 16 times 27. Still have the 18 out front. Now at this point, you can bring down the 18. If you realize 16 is a perfect square, bring the 4 out, but you still got to break down the 27, 9 and 3. Now you have another perfect square. So now you have negative 18 times the 4 times the 3, and then this square root of 3 stays underneath. Now what you'll do is go back, multiply these 3, and get negative 216 square root 3. I'm going to show you a better way. Notice after we multiplied this, I still had to do a factor tree. Okay? And what if you make a careless mistake when you're multiplying these three numbers? Then you're going to be messed up. So what's better, leave them unmultiplied. So let's do that. So let me rewrite the problem. So instead, let's do 3 square root 2 times negative 2 square root 8, and then 3 square root 27. Now, I still need to multiply all these outside things. So I could go ahead and do that and get negative 18. But now, let's work with what's under the radical. So I have a square root of 2. I'm going to break the 8 down. So the 8 would be 2 times 4, and then 2 and 2. So now for the 8, so let me bring this one down. So I have square root 2, and then this one has square root 2, square root 2, square root 2. That's for the 8. Then for the 27, 9 and 3, and then 3 and 3. So now I have the negative 18, and then I have all of the radicals individually broken down. So now what I'm going to do is go back and look for my pairs. So I have a pair of 2's, a 2 comes out. Another pair of 2's, a 2 comes out. A pair of 3's, a 3 comes out. This guy doesn't have a pair, leave him underneath. The 18 drops down, and now you're going to go back and you're going to multiply negative 18 times 2 times 2 times 3, and that gives you the negative 216 square root 3. So you can do it either way, just realize chances are you're going to have to factor it. Okay, next one. Again, I'm going to reduce the fraction. So really what I'm reducing is a fraction 6 over 90. I can divide them both by 6. So then this becomes 15. And then this simplifies to 1/15. And it's under a radical. So it's square root 1 over square root 15. But the square root of 1 is 1. So it's 15 over square root 15. Again, I have to rationalize. So I'm going to multiply the top and the bottom by the square root of 15. This becomes 15 square root 15 over 15, because I got a pair of 15s. Now, after you do this, if you can reduce this, see how I can divide both of these by 15 and they become 1s? So the final answer here is just the square root of 15. So if what comes out of the radical can be reduced, then you need to do that. Next, we're going to add and subtract. Remember to add and subtract square roots. They both need to have the same square root. So they both have a square root of 3. So then all I do is subtract the coefficients, because I'm pretending this is like an 8x minus 6x. So instead of writing 2x, I write 2 square root 3. So again, think of the square root of 3 like a variable. So you're just adding and subtracting the number in front. Now, on the next slide, if when you're adding and subtracting, if the numbers aren't the same, you would have to break them down first and then go back and add and subtract. So let's try the next slide. I'm just going to do one of these, and then I'm going to do this page tomorrow. So here, notice they're asking us to try to subtract these. I don't have the same radicals, but I could break down the square root of 24. I could break this down into 4 times 6. And then a 2 would come out, because I'd break it into 2 and 2, and this into 2 and 3, pair of 2's, and then put it back. So for this first one, this is going to become, oops, it's going to become negative 2, and then the 24, when it's broken down, becomes 2 square root 6. Then let me rewrite the rest of this problem. Now these two, on the first one, the negative 2 that was already out with the 2 that came out becomes a negative 4 square root 6. And then I rewrite this one. Now I can combine these radicals because they both have square root 6. So negative 4 minus 3 is negative 7 square root 6. And you're done. So I am going to finish these last examples tomorrow. So again, remember tonight, your homework is the P2B. That's your homework tonight. If you haven't turned in the P2B notes, turn those in. Do not turn these notes in. The P2C, we're going to finish these tomorrow, and then tomorrow night, your homework is the P2C. Any questions? All right, so we have like 2 minutes. The next one, I would need to break down the 45 and the 36, but I think it's going to take me too long before the bell rings, so I'm going to stop there, and I'll finish this tomorrow. I'm going to go ahead right now and finish the notes, so anybody who wants to look at this ahead of time, I am going to finish the video for this and do the rest of the slides, and I'll post it on YouTube this afternoon. All right, so for number 19, we need to break down the 45, and we need to break down the 36. Because remember, you cannot add radicals unless they have the same number under the square root or under the radical. So for the 45, I can break it into 9 times 5. And for the 36, it's 6 and 6. Now, if you realized that 36 was a perfect square, you wouldn't have to do this. Now, I could still break down those 6's, but I see I have a pair here, so I'm just going to bring them out. Over here, the 9, I could break it into 3 and 3. The 5 I'll bring down. And the 3 was already out. I've made a pair of 3's. So the 3 comes out. I'm going to multiply 7 and 6. And then now I'll go back and multiply 3 and 3. So 9 square root 5 plus 42. Notice the 42 does not have a square root, so this is my final answer. I can't add 9 and 42 because, again, 42 doesn't have the square root. For number 20, same idea here. I need to break down these square roots. 32, I'm going to break it into 16 times 2. You could also do 4 times 8. 63, I'm going to do 9 times 7. Now again, if you realize that you have perfect squares here and here, you can go and square root them, or you could break them down. I'm going to go ahead and break it down and make square root of 16 as a 4. Bring down this 3, bring down the radical, and then here square root of 9 is also 3, and then the 7. So now multiply that. 3 times 4 is 12, minus 4 times 3 is 12, square root 7. Now, notice the numbers outside of the square root are the same, but again, in order for me to add or subtract radicals, the numbers underneath here needed to be the same. So because they're different, this is my final answer. The next one, I'm multiplying 2 binomials. So if you remember your multiplication of binomials back from Algebra 1, your teacher might have either told you to distribute or to use the FOIL method. So what I'm going to do is I'm going to do first, 4 times 4 is 16. Then I'm going to do outside, or distribute it to the negative 11. Again, I can multiply a number by a radical. They don't have to be like, so it's just going to be negative 4 square root of 11. Then I'm going to do the inside, or distribute the positive 11 square root to 4. And then lastly, distribute the square root of 11 to the negative square root of 11. And again, I've made a pair. It comes out. A positive times a negative is a negative. Now, notice my 2 middle terms here cancel out when I go to add my like terms. Negative 4 square root 11 plus square root 4 of 11 is gone. So then 16 minus 11 is what's left, and my answer is 5. this is going to be leading us into conjugates, but this is actually where we would multiply a number by its opposite sign. So this is sort of like our difference of two squares back from Algebra 1. Okay, this is a binomial squared. Now on this one, I can't just distribute the exponent to both. Because it's got a minus sign in here, I'm actually going to write the binomial 2 times, and then I'm going to multiply. So 3 square root 7 minus square root of 3. Write it again, because it's squared. And now I can do FOIL or distributive property, however you learned it. So I would multiply first. So the two outside numbers, 3 times 3 is 9. And then square root 7 and square root 7, it's a pair of 7s, so it comes out. Next, I'm going to do the outside ones. Again, I can multiply an inside radical with an inside radical. So this becomes negative 3 square root 21. And then I'll do inside. So again, negative 3 square root 21. And then finally last, square root 3 times negative square root 3 times negative square root 3 is going to be plus 3. Let me go over this in white. So now I'm going to look to combine like terms. Notice this time the middle two terms do not cancel out. So this becomes negative 6 square root 21. And then I can also multiply this. This is a 63. And now I can also go back and add my numbers here that don't have radicals, 63 and 3. So this becomes 66 minus 6 square root 21. Again, the 66 does not have a radical, so this is my final answer. Now, the next slide is actually what we've been talking about all along. When we divide radicals, square roots must be eliminated from the denominator. So what we have to do is rationalize the denominator. And the way that you do that is you multiply the numerator and the denominator by the radical in the denominator or by the opposite expression. And we're going to see this with some binomials. Now, our goal is to make the denominator a perfect square. So the easiest way is you multiply it by the same radical that's down there. So then this becomes a 4 square root. Actually, let's just make it disappear instead of multiplying it. So again, we've got a pair of 2's, the 2 comes out. The 5 is out, the 2 is in, and that's that final answer. For this one, notice this last one, opposite expression. So I'm going to take my problem, and what I'm going to do is multiply it by the opposite sign. So what I need to do is FOIL the bottom and distribute the top. Now, whenever you multiply an expression by its opposite sign, essentially, again, what's going to happen is that outer and inner are going to cancel. So essentially, all you're doing here is first and last. But I'm going to walk you through all of it. So for the numerator, I need to distribute this 2 to the 2 and to the square root of 3. So 2 times 2 is 4 minus 2 square root 3. Then for the denominator, we're going to FOIL it just to show you that outer and inner will cancel. So when you do the multiply by the opposite expression, really all we're doing is first and last. So first, 2 times 2 is 4. Then outside gives me negative 2 square root 3. inside gives me positive 2 square root 3. And then last gives me square root 3 times square root 3 is negative 3, because we have a pair of 3's. Notice this in the middle cancels away. So if all you do on these is first and last, that'll give you your answer. So the denominator becomes 4 minus 3, which gives you 1. So then you have 4 minus 2 square root 3 over 1. And again, you don't need to write that 1, so just 4 minus 2 square root 3. Let me write it down here. And again, you can't subtract 4 minus 2 because the 4 does not have a square root of 3. Let me do 4 more examples, and then this video is done. So here, again, we need to rationalize. So to rationalize, we're going to multiply the top and the bottom by square root of 3. This becomes 7 square root 6. And then the denominator is a pair of 3's. And then you just take away the radical. This one, same thing. We're going to multiply top and bottom by square root 3. However, this square root 3 for the numerator needs to distribute to both. So this becomes 4 square root 3 plus square root 6 over 3. And that's our final answer. For 25, this is where we're going to do the opposite sign. So I'm going to do 3 minus square root 2, 3 minus square root 2. And again, remember when you do it to the denominator, just do first and last. 1 times both of these is just going to be 3 minus square root 2. So here, remember outer and inner will cancel. So just do first and just do last. So first is 3 times 3. Last will be just minus root 2. So 3 minus root 2 over 7. Now, if it's challenging for you at the beginning, you could do distribute, and you'll see that those middle 2 terms will cancel. And then the last example, again, I'm going to multiply by opposite sign. 1 plus root 2. I need a FOIL top. Again, the bottom, just do first and just do last. So the denominator is going to be 1 minus 2. But for the numerator, I'm going to FOIL and distribute for the whole thing. So 3 times 1 is 3. Then 3 times root 2 is 3 root 2. And then in here, it becomes root 2 times 1 is just root 2. And then last, root 2 times root 2 is just a 2. So now I can combine my like terms here in the middle. I assume a 1 in front of this. And then I can also combine my 3 and 2. So this will become 5 plus 4 square root 2 over negative 1. And then what I can do is divide both the top and the bottom by negative 1. So final answer here, negative 5 minus 4 square root 2. And that's it for section 2. So the homework that goes with this is the homework titled P.2C. And that's it.